Hello, good afternoon everyone. I welcome all of you to YouTube channel of Gradeup. So this is third portion of our structural analysis for BARC. So I welcome everyone. Everyone please join me as early as possible so that we can start our session. Here we will see few questions from ILD, then RCS, then some questions from matrix method. Am I audible to all of you? So join everyone together. Please join together as early as possible. Okay. Hello Swamiji. Hello Shruti. Please share it, and not getting comments on my system. Am I audible to you? Am I audible to you? Okay. Now please share it so that we can start our session as quickly as possible, right? Okay, now it's visible to me. So yesterday actually I gave one problem to all of you. Yesterday I gave you one problem to solve that. I hope all of you have solved that problem. So this is my small introduction regarding, and these are the batches which are going on for Vision 2022 and Vision 2023 in English and Hindi. And there is a mega mock challenge which is going on, which already happened on 4th August and then 7th and 14th 29th for BARC and GATE examination, right? Now it was the question which I gave it to you. Have you tried it? Have you tried it? Have you tried this one? So simply if you'll apply the moment distribution method, but before application of the moment distribution, one should understand here, this 10 kilonewton is acting. So what will be the df at this joint B, distribution factor at joint B? That is very simple, 1 at this side and 0 at that another side. So if you draw the moment distribution table, but before that he is saying that B is sinking. If joint B is going to get sinked by some amount, what will happen? What will happen? Due to the sinking, you know that due to the sinking of support B. Now if it is going to get sink, what will happen? This is the deflected shape of the beam which you will get it here, right? And then what? if the beam is rotating in clockwise direction, an anti-clockwise moment will be generated. And what will be the value of the anti-clockwise moment? 6 EI delta by L square, isn't it? 6 EI delta by L square this side and 6 EI delta by L square this side. That is the moment generated here. Okay, that is, yes, of course, 3 EI delta by L square, 6 EI delta by L square for 6 EI delta by L square, that's correct. So remember always, sometimes students do the mistake every time, that 6 EI delta, this is your hinge support. Hinge support does not create any moment. Several times I have seen that students are doing mistake. That's very nice. So no moment will be generated here. No moment will be generated here. Only 3 I delta by L square at this end. Only 3 I delta by L square at this end. No moment will be generated at this position. Right? Remember that one. Now write it down. Write it down. Write it down. But that's correct. Very correct. If you are applying the MD method, what is our major assumption? Every time we are considering, first of all, the beam is fixed. Then after consideration of fixed beam, we are approaching to the problem. Do you remember that one? That's correct one. What is the approach for the MD method? If you'll remember, if a sway will or sinking will happen here, this is the type of sinking will happen. And for the fixed beam, yes, if you have a clockwise rotation of the beam, an anti-clockwise moment will develop, and that moment is nothing but 6 Ci delta by L square. 6 Ci delta by L square. And here also you will get 6 Ci delta by L square. Right. Now that 6 Ci delta by L square, if you will count, if you will measure how much you will be getting it here. So that fixed end moment, if I will write it down, that moment at fixed end moment at A to B will be both are actually anti-clockwise, so I'll write down minus sign. Both will be minus sign, that is minus of 6 EI delta by L square. Delta already has been given. EI also, if you remember, if you see here, that 3i value is given. So 6 into E, and I is actually 3, so let it be 3i into delta. One second, I'll write down downside. 6 3 EI. Now delta value is already 48 by EI, and L square is nothing but 6 into 6, and here you have it EI. EI will get cancelled. Then you'll get 24 minus 24 kilonewton meter, you are getting it. Now remember that what is the approach for the MD method? That this is actually correct? No, it is not at all correct. Why? That is what we are doing now. Adjustment we'll do the adjustment in our MD table, isn't it? So let us do the adjustment on our MD table. So if you'll draw the MD table here, this is your joint A, this is your joint A, joint B, and then there is no joint C is already free. So for the joint B, you have a distribution factor, that is 1 here and 0 here, right? Now what are the fixed end moments? So that is what we are doing in our MD method. What are the fixed end moment we have? Fixed end moment, if you see, for the beam AB, there is no loading. There is no loading for the beam AB, right? There is no loading for the beam AB. Only due to the sinking, the moment is going to come. And that too, once again, remember, in an MD method, we are assuming both sides fixed. Every time, even for the loading also, we used to fix it. Now what will happen? Write it down whatever you got it. That is minus of 24 at A and minus of 24 at B. AB and BA. Then what? Then you have B to C. You have, that is C. If you have 10 kilonewton, that load is acting, it will generate a moment of 10 into 1 in the clockwise direction. And you can say for the beam BC, that is for BC, the minus 10 will be generated at this end. Now this is the scenario. What we'll do next? Now here you know that this is not the condition. It is not fixed from both sides. So now you'll do the adjustment. What kind of adjustment? You will balance the joint, because at a joint B, the moment is not at all balanced. If you'll add these two, you will get minus of 34. Isn't it? Then you take the plus sign, that is plus of 34, you apply it here. plus of 34 you apply it here, and half of that, as this is a fixed end, will come to this side, that is nothing but 17, and finally you'll get minus 7. That's all. The balancing of the joint has to be done. Both the moments should be balanced, right? If see, now calculate, you'll understand. Calculate how much you're getting it right now. If you'll calculate, finally you're getting minus 7 here, and here plus 10, and here minus 10. Now this is balanced. How? This is MBA is acting, that is C, clockwise direction, that is 10, and MBC is minus 10. Now the joint B is balanced. The way I did it, the way we used to do in our MD table, it will be balanced here. Did you get that? So he was asking about what is the final end moment at A, and final end moment at A will be 7, that's minus. Minus means what? Minus means what? That sign convention, if you remember in the MD method, that is anti-clockwise. Anti-clockwise means this side. This side. So minus 7 will be the final. So I can say that what it will do to the beam, it will be hogging, or maybe it is anti-clockwise. So 7 kilonewton meter anti-clockwise will the moment acting at the end A. Did you get that? Please let me know if you have any doubt, and please share it. Please do share and like button. Please share it. Okay, now let us move to the another problems. Here you have ILD. Which of the diagram is showing the correct ILD for the bending moment at C? Now, to get the bending moment at C, this is your, first of all, you should understand it is your indeterminate structure. So apply the Mueller-Wiritzler principle and tell me which one is the correct diagram showing the ILD for the bending moment, influence line diagram for the bending moment at C. This is the location of C at C. Which one will be the correct one? Which diagram represents the correct bending moment at C? ILD for the bending moment at C. Correct ILD for the bending moment at C. Yes. So now you apply, see, whenever it is asked either shear force ILD or bending moment ILD, always you provide the release. What is that release? Release means if you want to calculate or draw the ILD for the bending moment at C, you provide the hinge at this location. Now you are providing a release to the bending moment at C, and what will happen? Then after that you hold it in your hand the way I told you. Then after holding it in your hand, just provide a rotation or twist at this location, right? Provide now the way, suppose this is your thumb, provide it. That's all. What will happen? The bending moment diagram, if you see here, as it is your indeterminate structure, you know that a curve diagram will be coming out here. So the joint C, if it moves up, here you have a fixed support, you will get a curve, and a same curve will be continued to the joint F. This is your ILD. Correct option will be, achha, suppose if it will be asked what is the ILD for the shear force, at C. What will be the ILD for the shear force at C? At C, what will be the shear force ILD? So shear force ILD means what? You provide the shear release at this position. If you provide the shear release at this position, now due to the indeterminate structure, you will get a curve one. So bring it down and send it to up. That's all. And a curvilinear structure will be your showing the ILD for the shear force. That's all. Will be showing the ILD for the shear force. This is the ILD for the shear force at C. This is for the ILD for the shear force at C. Yes, it is parabola. Yes, Kasi. This is ILD for shear force at C. Now, can you tell me which one of the diagram is showing the correct ILD for the reaction at C? Just a second. Reaction at A. Which of the diagram is showing the correct ILD for the reaction at A? Once again, you need to understand it is your indeterminate structure. It is your indeterminate structure. For all the indeterminate type of structure, curvilinear diagram will be coming down. Can you tell me what will be the correct ILD for the reaction at A? So to get the reaction at A, what we have to do? Remove that stress function. That reaction is a stress function, isn't it? So whenever you have to draw the ILD, that particular stress function, you release it. That is what told by Mr. Mueller-Bristol. That is your Mueller-Bristol principle, right? Mueller-Bristol principle. And as per Mueller-Bristol principle, whenever whatever the ILD you want to draw it for the particular stress function, you release that particular stress function and provide the deformation by unit, and the deflected shape of the beam will give you the ILD. Deflected shape of the beam will give you the ILD. So the stress function, the reaction at C, you remove it, remove the function, and now you just lift it by unit. Lift it by unit. What will happen here if you lift it by unit? If you are trying to lift it, you know already you have a hinge at C and hinge at D. If D is not present, what will happen? Suppose if D is not there, if you are lifting this, it's a kind of single rod hinge at this situation. It is kind of seesaw for the students, for the children who plays in the park. It is a seesaw and it will be a straight line. If no support is at D, you will get the straight line by lifting this portion A, isn't it? That is the deflected shape of the beam. But as long as you have a D is fixed one, this will become indeterminate, and instead of getting the straight line, if you are trying to lift it, now C will behave like a partially fixed one. So lifting will create the curve portion, and that curve portion will be continued till D. Did you get that? And the curve portion will be continued till D. Now that will be the, so here this will be your correct ILD for the reaction at C. You need to always think about that like that. Both are curve, continuous curve. This is curve, no more straight line. So maybe I'm not drawing it properly, that, but it is not straight line. It is your curve. Are you able to understand that? It is your curve. Now what will be the correct ILD for the bending moment at C? Now C is here. This is the location for the C. What is the correct ILD for the bending moment at C? Same way I told you, just to keep your hands the way I told you. Keep your hands here and your thumbs. Okay, I'll just draw it in a separate one. Just I'll take the bigger one. This is your thumb, this is your hand. Now do that here. What will happen? Do the same at C, and what you'll get it? What type of deflected shape you will get? Because if he is asking what is the bending moment at C, just provide the hinge. That stress function, the bending moment, you release that bending moment by providing the internal hinge at that particular location. And then you hold it the way I am showing it to you. Then you just twist it. What will happen? Bend it. Now this will bend. Of course, it is a rigid joint, so it will get bent like this, isn't it? It will get bent like this. And then try to understand the characteristic of rigid joint. It will always maintain the angle. While it is maintaining the angle, what will happen? While maintaining the angle, the column for this side will make this angle, isn't it? So that 90 degree will be maintained here. 90 degree will be maintained here, and to maintain the 90 degree at this location, the column of right side will deflect like this. That is the deflected shape of the column to maintain 90 degree. Now to maintain 90 degree, this upper side column will be deflected like this, so that it can maintain 90 degree. That is the rigid joint, characteristic of your rigid joint. Here to maintain 90 degree, here to maintain 90 degree, it will be deflected outward side, then only it can maintain 90 degree here. Now to maintain 90 degree, the top horizontal beam will be deflected downward side, that is the proper ILD for bending moment at C. That is the proper ILD for the bending moment at C. If you have any doubt, please let me know. So only what you have to do, any indeterminate stress or structure, if you are any indeterminate frame or structure you are getting it, the deflected shape while you are drawing, you have to be careful. First of all, provide the particular stress release function, right? And after application, provide the deflection at that particular position, and you see that how the characteristic of rigid joint will be maintained, right? Now which one is showing the correct one? I think this one, right? This one is correct one. Yes, so B is the correct answer for this one. Did you get that? Now tell me, for the given beam, what will be the ordinate height? At C for the ILD of shear force at M? If you have to draw the shear force ILD, shear force at M, it is it is like, at a 2 meter distance from the support A. First of all, if he is asking about the ordinate, can you do that? Can you calculate this one? Yes, it is curvilinear. Yes. But for the determinate structure, the ILD will be always linear. So first of all, draw the shear force ILD at M. Shear force ILD for the shear force at M. So provide the shear release at M. And after providing that, bring it down, send it up. That's all. Bring it down, send it up. What will happen? What will be the deflected shape here? This is the deflected shape. This single portion of the beam will rotate about A, and the another portion of the beam, that is MBC, will rotate about B. And you will get the shape of the ILD for the shear force at M. This is the shape of the ILD for the shear force at M. Now what is the value here that you need to remember? This is your A by L and this is your B by L. Simply remember that A by L and B by L. A is 2 and B is 3. That's all. Now how to identify the ordinate? If you'll see that he's asking about what is the ordinate height at C, it means he's asking what is the ordinate height here at C. If you see here, B by L means what? How much? What is that one? If you see, that is B by L. What is that B by L? That is 3 by, sorry, B is 3 by L, 3 by 5, isn't it? That is this height. If you see, that is 3 by 5. And what is the length of this one? This 3. Then what will be the angle here, or tan theta? I will say 3 by 5 divided by 3. 3 by 5 divided by 3, it will become what? 1 by 5. 1 by 5 is your tan theta, or you can say that if 1 by 5 is the angle, you simply multiply the angle with the length and you will get it. That is the simplest way and the fastest way you can do that. Simply it will become 4 by 5. That's it. Simply it will become 4 by 5. You can do that by similar triangle, no problem at all. But I am saying that the way I'm explaining it, if you do this way, that will actually save your time. It is nothing but a similar triangle. You just go for the approach of the similar triangle, no problem in this. Did you get that? Now this is very nice. Example. Actually from here you learn a lot. From this diagram, from this particular problem, you will learn. Now what will be the correct match here? If you see, match the corresponding ILD with a list given here. Corresponding ILD. Match the corresponding ILD with list given here. See, one by one, if you want to see, you can always match. See, here only one is slightly difficult for the student. I'll tell you this one diagram. Can you say that? First option A is sometimes slightly difficult for the student, those who are drawing it. What is this one? I'll start from the option A. I'll start with the option A, right? Here, this option A, here, this diagram, what it represents actually. Now, if I'll ask you, what is the ILD just left to D? What is the ILD just left to D? Whenever the ILD for the shear force just left to D is asked, you do one thing. You come slightly more than D. You slightly come far away from the D and try to understand what kind of ILD you will be getting it. Are you listening me carefully? So see, whenever just left to D or right to D, a shear force ILD will be asked. You come slightly far away from that particular location. You slightly come far away from that particular location. Then you provide your displacement, right? Now the lower portion, if you are bringing it down, A, B, C will rotate about B, and you will get this kind of shape. Agree or not? You'll get this kind of shape. And here the portion DE will rotate about D, and you'll get this shape. You will get this shape. Agree? Agree? Now he is asking what is the ILD for shear force just left to D. Now to get the just left to D, now you consider whatever the section you have considered here, you just move towards D location. While you are moving towards D, what will happen? While you are moving towards D, what will happen here? Consider the section very near to D, and your diagram will look like this. I'm just almost at D, So now if you are very near to D, a very small portion will be there. You can just ignore this. And little bit. Now this portion, students have a confusion related to this portion. It will be constructed. My question is that if beam is there, if I'll say that no weight of the beam, a very small portion is given here, little deformation at this location. If you lift it, although you will not be able to identify through your naked eyes, but a large deflection will be considered and you can observe it. Are you able to understand this? A little bit deformation, if you do it here, it will go for the large one. For a similar triangle approach, you can understand, right? Now this is very small, which cannot be represented. So that is what we are doing it, where while creating a shear force ILD just left to D, we are actually not showing that small portion, and then we are showing this diagram. So this is the diagram for ILD just left to D. Are you able to understand this? Because this is one of the best part of your ILD. This is ILD for the shear force just left to D. If it is done, now this is 1A, this is 1, right? Now next to that, ILD shear force just right to D. What will be that? Just right to D. We'll see that one. Just right to D. It is your determinate structure, right? And just right to D, if you will come this side, what will happen? See, D is not your end hinge portion. So D has another hinge at B. So D will actually behave a partially fixed one. So what will happen if you will try to move? Suppose provide the stress, shear release at this location. Try to move this up and down. See how this will come down. See, if there is no B, of course the beam can rotate about D. And a straight beam will be coming like this. But the problem is that here you have another joint B, which will not allow the beam to go up. Joint B will not move up. Hence you cannot expect. What are the other possibilities? The other possibility is that if you are bringing it down, it may come like this. But it is once again a curve. For a determinate structure, one cannot expect the curve portion. So it is not possible. Are you getting my point? It is not possible. So what will happen? A complete upward side movement will be occurring at this location. A complete one unit displacement will be occurred at this location. Is it clear? So left side we cannot construct the ILD. Otherwise, if you will construct the ILD, it will become curve, which is not going to come in your determinate structure. So right side, a complete one will be coming at that. So if you'll just draw right to D, almost at the D we are drawing, and we are saying this is the ILD for shear force just right to D. ILD for the shear force just right to D. So this is the D option is for second one. Now which one? Third one, ILD for bending moment at C. ILD for the bending moment at C. Now you see, ILD for the bending moment at C. At C you provide the internal hinge, then you keep your hands the way I told you. Keep your hands the way I told you. Now if you just provide the rotate that joint C, provide the bend it here at C, what will happen? This portion of the beam straight is a single portion. About C it will rotate, about B it will rotate and it will be straight here. Then about D, this TDE will rotate and it will come like this. That is the bending moment ILD at the C. That is the diagram of bending moment ILD at C. Which one is this one? Here it is third one. Now of course B is the last one. So ILD for shear force at C. Shear force at C. What will be the ILD for shear force at C? What will be the ILD for shear force at C? Draw the ILD for shear force at C. Provide the stress, that function release, that shear release. Then send it upward, bring it downward. See, ABC will simply rotate about this joint, isn't it? About this point B, beam ABC will simply rotate, and this is the shape of the beam. Then about D, this beam also will simply rotate. Now this is the ILD for the shear force at C. This is the ILD for the shear force at C, which is already given here. So this one is nothing but your fourth one. So the correct option is A1, B2, A1, and where is B? B4, A1, B4, yes, A1, B4, and C3, and D2. So correct answer is D, option D. Did you get that? Now for the given beam, what will be the ordinate height at C? What will be the ordinate height at C for the ILD at, I think we have already solved this one. This one you please solve. Or if I'll ask, what is the, for the given C beam at ordinate height at C for the ILD of, I think we have done it for the bending moment. Oh no, we did it for the shear force. You do it for the bending moment. ILD for, if it has come, you do it. ILD for bending moment. Let us see. Bending moment at M. If you draw the ILD for the bending moment at M, what will be happening here? So bending moment at M, provide the release function, stress relief function. Then keep your hands the way I used to tell. Then what will happen? If you are keeping your hands, now provide that displacement, that rotation you provide here, and your beam will be actually MBC will be rotating about this joint B, that support B, and this is the deflected shape of your beam. Now the deflected shape of the beam will be representing your ILD for the bending moment at M. This is the correct ILD for the bending moment at M. Now if he's asking what is the ordinate height C, can you tell me what is the height at this location? That you need to remember. What is the ordinate height at this location? AB by L. Is it AB by L? So 2 into 3 by L, that is 2, 3 is 6 by 5. Here the height is 6 by 5, isn't it? 6 by 5. So I'll write it down, 6 by 5. Then what? If I'll say that what is this angle, 6 by 5 divided by 3. So 6 by 5 divided by 3 will become 2 by 5. So here it is 2 by 5. If it is 2 by 5, multiply with the length, and it will become 8 by 5. That's all. This is the correct one. All the options are not matching. Make sure this is 8 by 5. So the ordinate height is nothing but 8 by 5 here. Did you get that? No, it's not 6 by 5. The distance is given here is 4. So once you got the angles, these two angles are same. The ordinate height will be 8 by 5. Are you able to understand this one? Are you able to understand this? Then can you solve this one? A live load of 20 kilonewton per meter, 6 meter long, moves on a simply supported girder AB 12 meter long. This is your simply supported girder of 12 meter long, and a live load of 20 kilonewton per meter. A 6 meter long load is now actually moving. Now he is asking for a maximum bending moment to occur at 4 meter from left end A, that is A, from left end A at 4 meter distance, at a 4 meter distance at this location. At this location may be A, this is B, and this is C. So he is already providing the distance of C, that is your 4 meter. He is asking what is the maximum bending moment here, in such a way that your load will be kept where, how the load will be kept here. So load is continuously moving ahead, so I don't know where the load should be kept. So we'll take that maybe this distance I'll consider. Okay, I'll do a little bit. So let us consider that I'm going to keep the load in such a way that here the distance is x. Average loaded system we are adopting. How we are doing that? If it is x, it will be 6 minus x, isn't it? And the load is given, that intensity of load is given as 20 kilonewton per meter, 20 kilonewton per meter, isn't it? Now when you will get the maximum bending moment, so x by 4 is equal to 6 minus x by this distance is 8. This distance is 8. If you solve this one, how much you will get? 8x equals to 24 minus 4x, and it will become 12x equals to 24, and x is equal to 2. He's asking from the end A where the head of the load must be. This is the head of the load. Head of the load is here. Head of the load is here. Now I got x equal to 2, hence it is 4. Already it is 4 meter. At a 4 meter you want the maximum bending moment. Now you have to keep the load in this way so that you'll get the maximum bending moment at C. So the distance from the support A to the head of your loading will be nothing but 8 meter, isn't it? It will be your 8 meter. Did you get that? Now the stiffness coefficient at B. What will be the value of K11 at B? What will be the value of K11 at B? Can you do that? This is one of the simplest problem. What will be the value of K11 at B? This is your stiffness coefficient. You know that what is the meaning of that stiffness? See, stiffness matrix or stiffness coefficient of all the stiffness matrix, what it represents, what they represent. If you'll apply the load, unit load, what is the deformation? Right? Load required for unit deformation. So apply the load at 1, and what is the deformation at 1? That is the meaning of. So if you are applying the moment at that joint B, what is K11? So to rotate the AB, what is the total moment you need? 4 EI by L, isn't it? 4 EI by L by unit rotation. If you want to produce the unit rotation at B, how much effort you need to make? You just consider the AB portion like this. This is nothing but your prop cantilever, and you are applying some effort. You are asking me what effort I need to apply so that I can rotate this by unit amount. That is what you are asking, isn't it? That's what you are asking. So what effort I should apply so that I will get the unit rotation? That is nothing but your 4 EI by L, isn't it? Acha. The another portion, if you see for the BC, another portion is your simply supported both side hinge. So what you are asking, what is the effort I need to apply here so that I'll get a unit rotation? Now to get the unit rotation at B, once again for the simply supported one, how much you need to apply? That is 3 EI by L. Now this is the joint, a rigid joint here. If you want to rotate the joint completely by unit amount, the unit rotation if you want to apply, if you want to get it there, how much effort you need to apply, how much force you need to apply there? That is unit rotation. If you want to make sure for AB, you need to apply the effort 4 EI by L. Unit rotation if you are ensuring at BC, you need 3 EI by L. Summation of these two will become simply 7 EI by L. That is the effort or moment you need to apply there. That is your K11. Did you get that? Now what about this one? Which of the following element of the stiffness matrix are written correctly for the given structure? Out of which one is the correct? This also little bit lengthier one, but yes, good for practice. 2 by 2 matrix will generate for this given coordinate system. Is it correct? Is it correct? Yes, this one is correct, absolutely. Then what about others? K11 value. Can you find it out? What will be the K11? What will be the value of K12 and what will be the value of K22? Can you do that? To generate the stiffness matrix, although if the questions are going to come, it will be for only one stiffness coefficient. It will be only for one stiffness coefficient. Now, if you want to find it out what is K11, do one thing. How to do that stiffness matrix generation? So first of all, you consider the structure and you do one thing. You have to the translation at 1 and the rotation at 2. So if you are considering the any one of the coordinate, other coordinate you seize it. So consider the translation at 1 and seize the coordinate 2. While you are seizing the coordinate 2 means you are ensuring that no rotation at this joint, right? Now if no rotation you are ensuring, what will happen? What kind of deflected shape you will be getting it here? What kind of deflected shape you will be getting it here? So deflected shape of the beam will become, so no rotation, I'm ensuring here no rotation, right? Now this is the deflected shape of the beam. So apply the unit load in the direction of 1 and find it out what is the deformation. See, right? Can you do that? Sorry, apply the unit deformation at 1 and find out the forces at other coordinate. Load required for unit deformation. So what is the load required for unit deformation? Now I am providing the unit deformation that is in terms of translation here. In terms of translation. Now for any delta, if you want to make sure that if delta I want to move it due to the force applied at 1, the delta, if you see here, it is looking at like a sway of this sway, isn't it? The column is now actually kind of sway, and to sway it, you know already. I'm sorry. If the column is rotating in clockwise direction, and I think, should I draw another one? Now seize this one. Already we have seized. A column is if rotating in clockwise direction, anti-clockwise moment will develop. Isn't it? If they are rotating in clockwise, an anti-clockwise moment will develop. Now if the anti-clockwise moment will develop, what will be the value of that moment? 6EI delta by L square. Now what is the force? Will be developing here? That reaction will be developing at these two ends. They will develop to oppose the net moment. Net moment is 12EI delta by L square. Now they will be actually generating in such a way, the reaction in both the ends will be generating in such a way, they will oppose the net moment. Net moment is in anti-clockwise, so they will rotate in a clockwise. Together, see that two reactions together, they are rotating in a clockwise direction. What will be the value? That is 12EI delta by L cube. That net moment divided by length of the beam. Length of the beam is L. So 12EI delta by L cube. Already 6EI delta by L square here. 6EI delta by L square here. And 6EI delta by L square here. So net moment is how much? 12EI delta by L square divided by length of the beam will become 12EI delta by L cube. Now 12EI delta by L cube is here. 12EI delta by L cube is here. Did you get that? 12EI delta by L cube is here. Now what will be your K11? As simple as that, because in another support you do not have any restriction. Simply if you'll apply 12EI delta by L cube, 12EI delta by L cube, you're simply delta, you want to make the delta 1, unit deformation, make it 1. You need to apply you need to apply a force of 12 EI del 12 EI by L cube. That is nothing but your K11. To get the unit deformation in the direction of the coordinate 1, you need to apply the force. That K11 is nothing but your force, isn't it? The force required at 1 is 12 EI by L cube. So K11 is 12 EI by L cube. That is not correct. That is not correct here. Not correct at all, isn't it? Now what about K12? What about K12? So here from this one only I can get K21. What is the force generated due to the deformation given in the direction of coordinate 1? And then what we'll do? We'll apply the Maxwell reciprocal theorem. But what is that? K12 will be equal to K21. So directly I'll see already I have seen the deflected shape. Here I will calculate the K21, isn't it? K21, if you calculate what you are seeing here, K21, what is the meaning? What is the force generated in coordinate direction 2? Now if you see carefully, the coordinate direction 2 is actually in the clockwise direction, and the force generated is in anti-clockwise direction. That is, then minus sign will occur. Minus sign will occur. And what is that value also? That is nothing but 6 EI. 6 EI, delta is already 1 by L square. So the K21 is minus of 6 EI by L square. Minus of 6 EI by L square. And your K12 also will be minus of 6 EI by L square as per Maxwell reciprocal theorem. That is also not correct. That is also not correct. Now what about K22? What about K22? You apply the rotation at 2. I'll just draw it here. You apply the rotation at 2 and you see what are the forces generating in the coordinate direction 2 itself. Now apply the moment to rotate this joint. To rotate this joint, apply the moment. So coordinate direction 2 is given, apply the moment, rotate it. If you will rotate the joint by unit rotation, what will happen? See, a rigid joint always maintain the 90 degree. That is one. Can you see that? While I'm starting that deformation of the shape of the structure, that is a response you should understand. It will be maintaining the 90 degree. This is my first idea. This is my first idea about the deflected shape. If you will start rotating this joint, of course, first of all, it will maintain the 90 degree. A complete rotation of the joint will occur. Then what? Far end, whatever the support condition you have, that you see, that's all. Far end it is fixed, so of course, no rotation at that fixed end. No rotation at. This is the correct deflected shape of the frame. This is the correct deflected shape of the frame. Did you get that? Now, how much effort I need to apply to rotate it by unit amount? That unit radian rotation, if I want to make sure here, this is simply supported here. If you split it in a two different part, if you want to understand it, see that. This was your support here and this is support, just to provide it for more understanding. You want to rotate it by unit, yeah, do that. And then you split it, this one also, split it. So here suppose you have a support and this is your column and it is fixed. You are applying the moment like this, so it will be rotating like this maybe. No. Now how much effort you need to rotate this simply supported beam? You need 3 EI by L, isn't it? And here you need 4 EI by L. So total effort need by you, total effort is how much? 4 plus 3, that is 7 EI by L. If you will apply 7 EI by L here, that will rotate this joint by unit radian. So that K22, yes, it is correct one. So hence 1 and 4 are only correct and no option is given. I'm sorry for that one. So only 1 and 4 are correct. Only 1 and 4 are correct, right? Only maybe this one, only 1 and 4 are correct. Any doubt here? Did you get that? This is your simply supported, so here you need to apply the effort 3 EI by L. That is the force or moment you need to apply here, and here you need to apply amount of 4 EI by L. So total effort needed here is 7 EI by L for unit rotation. Is it clear? Now what about this one? What will be the horizontal thrust for a given 3-inch circular segment arch if W equals to 4 kilonewton per meter? If weight that acting is 4 kilonewton per meter, what will be the horizontal thrust? How you will calculate that? See, whenever you will get the 3-inch arch, do not worry. It is nothing but your determinate, like it is your beam only. The way you do it, all the static equilibrium conditions you can apply, and 3-inch arch you can apply the bending moment at this location also equal to 0. That's all. That's all. Did you get that? So it is very simple. It is very simple. Now if W is 4, how will do that? So 4 kilonewton per meter, right? Total load is how much? Total load is 4 into this height is 10. Total is 40. 40 is acting at half of that, that is 5. So it is 200. Now it is a 200 which is rotating. What is the reaction you will get? So clockwise moment you have at that 200. Of course the reaction will be against the moment. Can you do that reaction? You can use your equilibrium conditions also. If you want to utilize the equilibrium condition, let me do that through that one also. Or you can simply do that. See, 4 is the intensity of the load. 4 into 10 is the total load acting at almost mid. That is 5, right? So 20 is acting at 5 distance. So 20 into 5, sorry, 4 into 10 is 40. Sorry, 4 into 10 is 40. 40 is acting at 5, so it will become 200. So total moment in a clockwise direction you have 200. So they will be generating that net moment divided by length of the beam. If you do 200 divided by 40, 200 divided, yes, that 0 you will get 5. So 5 kilonewton will be acting. That is the reaction here, and it will be, see, if it is rotating clockwise, they will rotate in anti-clockwise. That is the reaction you will be getting it here. Are you able to understand that? Are you able to understand that reaction? You need to generate that to make it fast. Otherwise, you want to do the simple equilibrium condition analysis, that also you can do it. Is it 10? Is it 10 it is coming? How? 4 into 10, that is 40. Or let us do that. Let us do that then. See, reaction at A and reaction at B. Right? Now reaction at A and B, you'll do, take that one, RA plus RB is equal to 0. RA plus RB equal to 0, isn't it? Then what? Take the moment at maybe A. Summation of moment at A equal to 0. How much will be getting it? Summation of moment at A. So RB into 40 is rotating anti-clockwise state, minus, no problem. Then what? The horizontal thrust are passing by this one only, so don't consider it. And you don't have, yeah, that there is a load, that 4 into 10, that is 40. 40 is acting at 5 distance. So 40 into 5 is rotating once again clockwise, right? Clockwise. So plus 40 into 5 equal to 0. RB, how much you got it now? See here. 40 into 5 by 40, you are getting 40. So you are getting 5. Now, did you see that? How much you are getting it? Thrust will get it. I'm saying it that how you can get the reaction easily. RB will get 5 now, RA will become minus 5. That is what I am showing it to you. RA you have considered like this, no, that is why you are getting minus sign. So either you do through the normal equilibrium condition, or you do the way I am saying it to you. The total net moment you calculate, and just you find out the reaction by net moment divided by length of the beam. Net moment divided by length of the beam. That's all. Now he is asking about the horizontal thrust, isn't it? Now horizontal thrust, always remember bending moment at crown. Take the bending moment at crown. It is 0, no? It is 0. So stand here and take the bending moment at crown 0. So bending moment at crown is equal to 0. See towards right side. You have horizontal thrust here and you have a reaction. That's all. You do not have anything else. So simple. It is very simple. RB into, what is the distance from here? 20. So RB into 20 is rotating. Oh, it is actually creating kind of sagging. So if I'm taking the nature of this RB as a positive, H will create a negative because the nature will be opposite to that. So minus of H into what is the distance. Always try to extend the line of action of the force so that you will not confuse during the time of examination. This is the perpendicular distance, that is 10. This is the perpendicular distance, that is 10. So H into 10 equals to 0. And RB value you have how much? RB you already have that 5, isn't it? Now how much H will become? H will be minus will get cancelled. 20 into 5 divided by 10. Now 10 2s are 20, 2 5s are 10. That's all. 10. 10 kilonewton is the horizontal thrust at your support. 10 kilonewton is the horizontal thrust at your support. Did you get that? How to solve this one? A cable of span length. This is simply I actually used to give. If it is kind of formula based also, but one can do it very easily. If he is asking about what is the maximum tension, see maximum tension, where you will get it, where you will get the maximum tension, where you will get the maximum tension. If the cable is carrying the load, you will get the maximum tension at this location, tension in the string. This is the maximum tension zone. Now how to get the maximum tension at this location? So consider maybe this is your horizontal one, this is your horizontal one, H suppose, and this is your vertical one, vertical at, suppose this is joint A, so this is vertical at A. So resultant of the horizontal and vertical will give you the tension. That is what maximum tension will be getting here, and you will get minimum tension at the dip. So if you want to calculate the maximum tension, you calculate first of all what is H and what is V. V is very simple. If it is UDL, if it is having the UDL, so total load is how much? UDL. Suppose W is the kilonewton meter, the intensity, W kilonewton meter is the intensity. What will happen here? W into L is the total load, divided by 2 is the VA and VB. That is very simple. VA, this is symmetrical, right? So VA equals to VB equals to WL by 2. That's all. Now VA, I got it. How you will get the horizontal thrust? You stand at maybe at the mid portion, as it is symmetrical one. Suppose I will take the bending moment at C here, 0. Bending moment at FC on a string, actually bending moment everywhere it is 0, isn't it? Everywhere it is 0. So if you stand here and you will consider the bending moment at C must be equal to 0, what is the equation you are going to write it down? So bending moment at C must be equal to 0. Now you see here, H into this dip, H into this dip, that is maybe H. So horizontal thrust H towards left side, H into the perpendicular distance H. It is rotating in a anti-clockwise, so let it minus sign. Then VA is rotating clockwise, so plus of VA into what is this distance, that is L by 2, and then there is a UDL, that W into L by 2 is the total load. Now this is also going to rotate anti-clockwise, so minus of W into L by 2 is the total load, and it is acting at L by 4. Isn't it? It is acting at L by 4. Now VA already we got it, WL by 2, so put it there, and finally how much H you will get? Minus H of H, then plus WL square by 2 minus WL square by 8 is equal to 0, and H will become how much? Can you tell me? WL square by 8H, is it? Can you see that? How much you are getting it? WL square by 8H, isn't it? Now that WL square by 8H already got it. Now what is that? Resultant, simply you got tension. Maximum tension will be H square plus VA square. Now simply you can identify this one. VA square already you have, that is WL by 2 whole square, and then plus H is your WL square by 8H whole square under root. Simplify a little bit here and there. Simplify. You can take WL by 2 as a common. You can take WL by 2 as a common. If you take the WL by 2 as a common, it will come out from the under root also, and you will get here it is a 1, and plus you will get WL by 2 has came out, so you will get one more L will be there, that is L square. You will be having that L square, so that W has gone, L square will be there, then 2 has gone, 4 will be there, so L square by 8 square, no, so you have taken only 2, so kitna milega? 32. You have taken actually 4, so 64 by 4, it will become how much? WL square by 16, 16h square. W square by 16h square. That's all. So simplification, if you do simplify, you'll just see option A. So it is actually easy one. But the thing is that you need to remember, it is simplest one. Maximum tension you will get it here, and to get the maximum tension, the vertical and the horizontal must be calculated. Once you will calculate the vertical and horizontal, take the resultant of these two and you will get the maximum tension. Sometimes this is used a direct formula. Sometimes this one we are using it for as a direct formula. Did you get that? So that's all from my side, and these are the star faculty of the Gradeup, and from tomorrow onwards I will be starting that strength of material. A lot of questions are coming for the strength of material. Do not miss the session at 3 p.m. every day. At 3 p.m. every day, please do not miss it. We'll be meeting for the strength of material. So from tomorrow, please be sure we all are meeting at 3 p.m. for strength of material. Thank you everyone.